Assalamualaikum warahmatullahi wabarakatuh, and very good afternoon to everyone. So, first of all, I would like to express my respect and gratitude to the examination community, Dr. Chandra Devi, and also Dr. Sigit Adinugroho, and to my supervisors, Dr. Novanto Yudhistira and Professor Yuta Nakashima. Thank you very much for your time and for the opportunity to present my thesis proposal today. So my name is Manotadion, and the title of my proposal is Tethered Free Energy Flow, or TFF for short. It is about test-time adaptation. In short, how a model can keep performing well even when the data it changes after training. So with your permission, allow me to begin. So here is the plan today. First, I will talk about the problem, what happens when the data shifts. Then I will show the existing methods, essentially a map of what has been tried before. And after that, my method and the two main theory results. And at the end, some early experiments and the schedule of my research setting. So allow me to begin. Okay, so this is the main problem. So when we train a model, it works great on the training data, right? But in the real world, the data can look very different. So for example, the images can be blurry, noisy, or foggy, etc. This is what we call distribution shift. The test data is shifted away from what the model is learned. And as you can see here, like this image, when this happens, the accuracy drops a lot. And on this benchmark called Cipher 10 corruptions, the model falls around 52%, which is a lot, I think. And the offshore fix will be to retrain the model, but we cannot, right? Because we don't have labels or new data, and often we also cannot even access the original training data anymore. So the model has to adapt by itself online while it's running without any labels. And the tricky part is with no labels, the only thing the model can rely on is its own confidence. So that is the main problem of this research talk. Um, so before presenting my method, I would like to show what has already been done. There are basically four families of methods here. The first one, patch norm adapt. It refreshes the patch norm statistic. So patch norm is actually like a layer inside the network that normalizes the data, and this method updates its numbers for the new data. So it's simple, but it doesn't really learn anything, and no wake update also. And then the second family is entropy based, like 10. And entropy here means how unsure the model is. So this method push the model to be more sure of its predictions. And then the third is source retention, like CoTTA. This source retention means it keep pulling the model back toward the original one. So when the corruption is continuing, it doesn't drift too far from the original source. And then the fourth is energy based, like TEA. This is the family of my work belongs to. Now, the interesting part is this red line at the bottom. All of these are actually fighting the same problem, I think. called self-reinforcing loop. So because the model learns from its own confidence, it can start believing in its own mistakes more and more, kind of like an echo in a cave that grows louder and louder. So every method here, and also every method here adds some trick to stop that. But the tricks are all hand tuned or heuristic. Then the next slide is why we use the energy. So let me first look at the left side of this figure in the slide. We have the entropy objective, the thing that most methods use actually. The problem is in the entropy objective, once the model becomes confident, the gradient basically becomes zero. So nothing more happens, and the failure boundary is never really reached. And then on the right side, we have energy objective. So energy in here means so something like maybe something like this. So it is how normal or how strange an input looks to the model. So low energy means normal. High energy means it looks strange, and the energy is only limited from below by a term called the partition function, which is never recomputed during testing. So the energy can keep dropping and dropping with no floor, something like that. And then honestly, with that condition, it's actually helpful for us because it means the failure point is real and actually happens with the extreme energy values. So because of that, we can actually study it. Not like the entropy one when we cannot because it really never even get there or reach the floor, something like that. Then um, um, so then if the energy can keep dropping, what normally stops it? And the answer is a mechanism called the negative phase. So energy models, training actually has two parts: the positive phase that pushes energy down on real data, and the negative phase that pushes it back up on the imagined sample. So together they stay balanced, and the negative phase is basically the wall that keeps the energy from collapsing. But there are two main problems with this method. First, it is expensive. It is a slow sampling process called SGLT or stochastic gradient line driven dynamics. And second, on Kindle streams, meaning when corruptions keep coming one after another, it can still fail. So people started dropping it, but uh, but here is the thing in this red line. If you drop the negative phase, you remove the regularizer or the wall. So now nothing is holding the energy in check, and uh, and also nobody knows what replaces it or when it is safe, even safe to do that. And that right there is the gap of my thesis that I want to fill. So from that gap, I have four research questions. The first is about stability. So can we adapt on continuous streams without the negative phase and not diverge? And then the second is about which part actually does the work. And the third one is the theory. Uh, also, can we describe the behavior with a clean formula, not just working, something like that. And the fourth is about calibration. Is the model still honest about its confidence? And then also, as you can see on the right, all four come from one root, and the self-reinforcing loop that I mentioned before. Two of them ask something like this: does it stay bounded, and then one thing and then one asks what is really needed, and then can we trust the output, something that in the simple way. So the whole thesis comes down to this one question, I think. So if we drop the negative phase, what keeps the energy bounded, and when is that safe? This is the answer that my work proposes. And then this is my method, uh, TFF, or tether free energy flow. Um, so TFF is actually a reformulation. What I mean is, instead of seeing the adaptation as an algorithm or a list of steps, I see it as a stochastic process. So it is a system that settles into a stable state over time. Um, and as you can see on this diagram, the test batch goes through the backbone, and at each stage we compute an energy, we combine them, take one gradient step to lower the energy, and then there is this descent, and this part, the tether randomly pulls some parameters back to the original source values. Bernoulli here means a coin flip. So each parameter can goes back with some probability of p, something like that. And the point in this, so because I set it up as a process, I can actually derive its stable state with mathematics. So the previous method cannot do that because uh, it was never written as this kind of object, I think. And dropping the negative phase, that is simply false out of consequence of this reformulation. And this is a closer look at that single update. On the left is the small full picture of the method before, and on the right side is the zoom in. So in one step, two things happen at the same time. First, the data pushes the parameters away from the source, and that is the energy descent or the push. So second, the tether pulls them back, or we can say pull. And when you write these two together, you get this recursion at the bottom. A formula for how far the parameters drift each step. Drifts mean how far the parameters wander from the original. And the key point is, this formula only exists because the tether is inside the update, not bolted on the side sublet. And that is what makes the whole analysis possible. And then this slide is slightly more technical, I think, but the idea is simple. When the model updates, each class gets pushed based on how likely the model thinks it is. This is the gradient, the direction of change. Both energy and entropy share this part. Um, but entropy has an extra term that makes the push shrink to zero once the model is confident. There is the vanishing eye. I mentioned this is the vanishing eye method I mentioned earlier, and energy does not have the term. So the energy gradient keeps working even when the model is very sure. As we can see, there is the real difference between these two. Now, the first theory result, proposition one. A proposition is a proven statement, a bit smaller than a theorem. And what it says is this: as long as the parameters stay inside a certain region around the source, I call it the ball of PR, a kind of safe zone around the original model. Then the energy stays bounded. It cannot blow up uh, to n not a number or extreme value, something like that. Then, and if it stays bounded, then we do not need the negative phase at all in this zone. So that wall we remove, it turns out we do not need it as long as we stay near source. And one honest note, that the size of this zone are, I treat it a bit abstractly and check it in experiments. I do not compute it exactly step by step. And this is the main theory result, theorem 2. Theorem is a bigger proven result. So here I actually derive in closed form, meaning an exact formula, how the parameters behave in the long run. Think of it as two forces reaching a balance. The data pushing out with the strength of eta times the gradient norm, and the tether pulling back with strength of p. Then they settle at an equilibrium state, and the average drift in this formula here. And from this, I get a threshold I call p star, the small stator string that still keeps things safe. And to be honest, the theorem explains the direction and the scaling very well. The exact result value I still pin down with extra experiment. Then this is how I evaluate everything. I use Cipher 10 corruption at severity 5 for now, the hardest corruption level, with 50 different corruption types, to architecture, extend 80, and whether one count white ResNet, standard optimizer settings, and I compare against the usual baselines and the source model, version of Adaptation, NTA, and etc. Then I measure accuracy, but also calibration, memory time, and the drift and energy behavior. Then now some early results. This is the decomposition. I work from the previous method to mine one change at a time, so I can see exactly which change matters. And the answer is the kind of clear, like the big jump, plus 2.68 points and about 540 times faster, comes from just one thing, which is replacing the expensive negative phase with the direct positive phase. And the other phases is the noise and the model stage part, which is adding basically nothing that measurable. Then the positive phase is also the real worker here. So the rest is simply came along. Then this slide shows the stability directly. Each line here is the energy over time, and you can see two clear groups. The green ones stay flat and low. These are bounded and they behave nicely, I think. And the red ones plunge down to extreme values and then hit none or not a number, which means the computation effectively breaks down. So without the tether, the energy can escapes, and with the tether, my method stays stable across all 15 corruption. And this is exactly what the theory predicted. So to summarize the early evidence of all four research questions, uh, so all four research questions already have some support. Stability, yes, stable on board architecture. And research question two, uh, we know that the operative component is the positive phase. And then the research question three, we know that the closed form formula matches the measurements. For research question four, we know that we use the expected calibration error, which measures whether the model's confidence matches its real accuracy. It is lower, meaning better than 10 NTA. Then there is also a newer thread that I'm still working on. I found that the threshold P star can actually be predicted with this simple formula derived from theorem 2. From quantities I can measure while the model is running, and this fits really well. The slope is about 1.15 across two different settings, but it is still developing, so it does not fully generalize to other loss types yet. But I think it looks promising. Uh, to summarize my contributions, first the TFF method itself, then the source data that will directly into the update rather than edit on the site, then the closed form stability analysis, and then the control decomposition that shows what really works. And the scope, to be clear, is for now just cipher 10 corruption to CNN architecture and this corruption type of shift. So naturally there are some limitations. I only test on synthetic corruption and two CNN models, so I cannot yet claim it generalizes everywhere. And also my theory also assumes a limited time horizon, and the data strength P is a bit sensitive to the architecture. And then for the future, I want to try a bigger dataset like ImageNet-C and or Cipher 100. And also, I think I must use a transformer-based model like VIT, etc. And then I want to predict that threshold P star directly from the loss curvature. And this is my timeline for the rest of the work. I think just roughly just 8 months maybe. So from finishing the implementation and the experiments to the drift analysis and finally wrapping everything up. And to close the loop, so everything here comes back to one idea. Adaptation without labels is a self-reinforcing process, and I examine it from a few sites, and the early results I think already support all of our questions. From the last, these are my references. Thank you very much for your attention. I will be glad to answer any questions.